Mahamanav Aerospace and Research Exploration Private Limited. This is an internship program on avionics presented by Priyanka Ayali. Direct reading compass. This includes the topic gyroscope, altitude indicator, heading indicator, turn and slip indicator. Introduction. Gyroscopic flight instruments of some description are used in most general aviation aircraft and in older commercial aircraft. Examples of such instrument include the attitude indicator, heading indicator and turn coordinator, that is turn and slip indicators. The gyroscopes within the instruments are usually electrically or vacuum driven and make use of the basic gyroscopic principles to display the attitude of the aircraft. In more modern installations, mechanical gyroscopes have been replaced by laser gyros. Have a look at this figure given below. The gyroscopic principles. The principal characteristic of a gyro that makes it suitable for in the attitude instrument is the rigidity in space. Secondary gyroscopic principle that must be understood and compensated for as necessary is precision. The explanation of the term is as follows. Rigidity in space. The primary trait of the spinning gyro rotor is rigidity in space, otherwise known as the gyroscopic inertia. As stated in Newton's first law, a body in a motion tends to move in a constant speed and direction unless acted upon by an external force. The spinning rotor inside the gyroscopic instrument maintains a constant attitude in space so long no external force acts to change its motion. This stability will increase in the proportion to any increase in the mass or the speed of the rotor. As a consequence, the rotor in gyroscopic aircraft instruments are constructed of heavy materials and are designed to spin at rates in the order of 10,000 to 15,000 revolutions per minute. Attitude and heading indicator use gyros as an unchanging reference in the space. That is, once the rotor is spinning, it maintains a constant position with respect to the horizon or the direction. The rotor of the universally mounted gyro remains in the same position as the surrounding circular frames or gimbals are moved. For all the intents, this allows the aircraft to rotate around the gyro without changing the position of the rotor. The aircraft's attitude or heading can thus be compared to the rotor to enable the instrument to display the actual attitude or a direction. Precision. Precision is the tilting or turning of the rotor axis as a result of external forces. When a deflective force is applied to a stationary gyro rotor, the rotor will move in the direction of the force. However, when the same force is applied to the rim of the spinning rotor, the force causes the rotor to move as though the force had been applied to a point of 90 degrees around the rim in the direction of the rotation. This turning movement of precision places the rotor in a new plane of rotation which is parallel to the force. Precision is caused by both frictions within the gyro and by the aircraft maneuvering inclusive of the turns, acceleration and cross-checking the heading indicator or directional gyro with the magnetic compass and making the appropriate corrections should be accomplished on a regular basis. The gyro power sources. Gyroscopic instruments are generally powered either electrically or pneumatically. In the former case, the rotor is incorporated as the armature of an electric motor, while in the latter, a vacuum pump driven by the engine reduces the pressure within the instrument case. Filtered air from the cabin is drawn into the instrument, accelerated and directed at the rotor wheel to cause it to turn. Vacuum instruments are susceptible to underreading due to the rotor deceleration should have the vacuum pressure drop and are not suitable for the high altitude installations. Altitude indicator. Introduction. The altitude indicator is one of the 6 basic flight instruments found in any cockpit. At a glance, it gives the pilot a clear picture of the aircraft's relative position to the Earth's horizon. With one simple dial, the pilot can see whether the plane is climbing, banking, or descending. Without it, a pilot has to cobble together a picture of the aircraft's attitude from other instruments such as the turn and bank indicator and vertical speed indicator. Have a look at this figure right here. This figure shows various different terms of the indicator. Types of attitude indicator. Traditional attitude indicator. Much general aviation aircraft fly with the vacuum or air-powered gyroscopic attitude indicator. A vacuum is pulled or air blown to spin the gyroscope inside the instrument case. Vacuum gyros are susceptible to contamination and leaks in the system that can result in inaccurate indication. Depending on the age of the instrument, it may have limitations on the degrees of bank and pitch that is able to display without tumbling. Newer units do not have the tumbling problem. Electric attitude indicators use an electrically driven gyroscope instead of a vacuum. Electric indicators are commonly used as a backup instrument with the battery power in the event of vacuum indicator failure. They usually don't have the same limitations as the traditional units but have a cage lever to cage the gyro during the maneuvers to avoid any lengthy erection process. Digital altitude indicator. New FAA policies allow the replacement of a vacuum driven instrument with an electronic version of the primary use. This means digital altitude indicators can be a part of glass cockpit installation, changing the way pilots scan the instrument panel by combining several traditional instruments into one unit. Solid state electronics mean the digital versions do not have a pitch and bank restrictions. The systems also contain battery backup power in case the aircraft's electrical system fails. Heading indicator. The heading indicator, also called as HI, is a flight instrument used in an aircraft to inform the pilot of the aircraft's heading. It is sometimes referred by its older names such as the directional gyro or DG, also UK usage in direction indicator or D. Operational working. The heading indicator works using a gyroscope tied by an erection mechanism to the aircraft yawing plane, that is, the plane defined by longitudinal and horizontal axes of the aircraft. As such, any configuration of the aircraft yawing plane that does not match the local Earth horizontal results in an indication in error. The heading indicator is arranged such that the gyro axis is used to drive the display, which consists of a circular compass card calibrated in degrees. The gyroscope is spun either electrically or using filtered airflow from a suction pump, sometimes a pressure pump in high altitude aircraft driven from the aircraft's engine. Because the earth rotates, 15 degree per hour apparent drift, and because of the small accumulated errors caused by imperfect balancing of the gyro, the heading indicator will drift over time like a real drift and must be reset using a magnetic compass periodically. The apparent drift is predicted by omega sine latitude and will thus be greatest over of the poles. Counter the effect of earth rate drift, a latitude nut can be set on the ground only, which induces a hopefully equal and opposite real wander in the gyroscope. Otherwise, it would be necessary to manually read the direction indicator once each 10 to 15 minutes during routine in-flight checks. Failure to do this is a common source of navigation error among new pilots. Another sort of apparent drift exists in the form of transport wander caused by the aircraft movement and the convergence in the meridian lines towards the poles. It equals the course change along a great circle orthodrome of flight path. Turn and slip indicator. The turn indicator is a gyroscopic instrument that works on the principle of precision. The gyro is mounted on a gimbal. The gyro's rotational axis is in line with the lateral, that is pitch axis of the aircraft, while the gimbal has a limited freedom around the longitudinal or the roll axis of the aircraft. Working. As the aircraft yaws, a torque force is applied to the gyro around the vertical axis, aircraft yaw, which causes the gyro precision around the roll axis. The gyro spins on the axis that is 90 degrees relative to the direction of the applied yaw torque force. The gyro and gimbal rotate around the roll axis with a limited freedom against the calibrated spring. The torque forced against the spring reaches an equilibrium, and the angle that the gimbal and gyro become positioned is directly connected to the display needle, thereby indicating the rate of turn. In the turn coordinator, the gyro is canted 30 degrees from the horizontal so that it responds to roll as well as yaw. The display contains hash marks for the pilot's reference during a turn. When the needle is lined up with a hash mark, the aircraft is performing a standard rate turn, which is defined as 3 degrees per second, known as in some countries as rate 1. This translates to 2 minutes per 360 degrees of turn, a complete circle. Indicators are marked as their sensitivity with 2-minute turn for those whose hash marks correspond to the standard rate or 2-minute turn, and a 4-minute turn for those used in the faster aircraft that show a half standard rate or 4-minute turn. The supersonic Concorde jet aircraft and many other military jets are examples of the aircrafts that use 4-minute turn indicator. The hash marks are sometimes called as doghouses because of their distinct shape on the various makes of the turn indicator. Under instrument flight rules, using these figures allow a pilot to perform timed turns in order to conform with the required air traffic pattern. For a change of heading of 90 degrees, a turn lasting 30 seconds would be required to perform a standard rate or rate 1 turn. Inclinometer. Coordinated flight indication is obtained by using an inclinometer, which is recognized as the ball in a tube. An inclinometer contains a ball sealed inside a curved glass tube, which also contains a liquid to act as a damping medium. The original form of the indicator is in the effect of a spirit level with the tube curved in the opposite direction and a ball replacing the bubble. In some early aircraft, the indicator was merely pendulum with a dash pot of damping. The ball gives an indication of the whether the aircraft is slipping, skidding, or in coordinated flight. The ball's movement is caused by the force of gravity and the aircraft's centripetal acceleration. When the ball is centered in the middle of the tube, the aircraft is said to be in coordinated flight. If the ball is on the inside, wing downside of the turn, the aircraft is slipping. And finally, when the ball is on the outside, wing upside of the turn, the aircraft is skidding. A simple alternative to the balance indicator used on gliders is the yaw string, which allows the pilot to simply view the string's movements as a rudimentary indication of the aircraft balance. Turn coordinator. The turn coordinator TC is a further development of the turn and slip indicator TS, with a major difference being the display and the axis upon which the gimbal is mounted. The display is that of a miniature airplane as seen from behind. This looks similar to that of an attitude indicator. No pitch information is usually written on the instrument to avoid confusion regarding the aircraft's pitch, which can be obtained from the artificial horizon instrument. In contrast to the TS, the TC's gimbal is pitched up to 30 degrees from the transverse axis. This causes the instrument to the respond, roll as well as yaw. This allows the instrument to display a change more quickly as it will react to the change in the roll balance before the aircraft has even begun to yaw. Although this instrument reacts to the changes in aircraft's roll, it does not display the roll attitude. The turn coordinator may be used as a performance instrument when the attitude indicator has failed. This is called partial panel operation. It can be unnecessarily difficult or even impossible if the pilot does not understand that the instrument is showing roll rates as well as the turn rates. The usefulness is also impaired if the internal dashboard is worn out. The latter case is the instrument underdamped and in turbulence will indicate large full-scale deflection to the left and right, all of which the actually roll rate responses. Uses. Slipping and skidding within a turn is sometimes referred to as a sloppy turn due to the perceptive discomfort it can cause the pilot and passengers. When the aircraft is in a balanced turn, ball is centered, passengers experience gravity directly in the line with their seat, that is force perpendicular to a seat. With a well balanced turn, passengers may not even realize the aircraft is turning unless they are viewing objects outside the aircraft. While aircraft slipping and skidding are often undesired in an usual turn that maintains altitude, slipping of the aircraft can be used for practical purpose. Intentionally putting the aircraft into a slip is used as a forward slip and a side slip. These slips are performed by applying opposite inputs of the aileron and the rudder controls. A forward slip allows a pilot to quickly drop altitude without gaining unnecessary speed, while a side slip is one method utilized to perform a crosswind landing. This was all about the direct reading compass. Thank you.